Welcome back. In this lesson, we are going to study the common collector amplifier, often just called the CC amplifier, using the H parameter model. It's one of the three basic single-stage bipolar junction transistor amplifiers alongside the common emitter and common base designs. By the end of this session, you will understand why this configuration is prized for its high input impedance, its near unity voltage gain, and why engineers often call it a buffer stage. Let's get started. Before we dive in, let's look at what you should be able to do once you completed this section. First, describe and analyze the operation of the common collector amplifier and discuss the emitter-follower amplifier. Second, analyze the amplifier for voltage gain and explain exactly what we mean by the term emitter-follower. Third, discuss and calculate input resistance. Fourth, determine output resistance. Fifth, determine current gain and power gain delivered to the load. And finally, we'll extend these ideas to two special two-transistor configurations, the Darlington pair and the Sziklai pair. That's a lot of ground to cover, so let's begin. The common collector amplifier is usually referred to as an emitter-follower. The input signal is applied to the base through a coupling capacitor, and the output signal is taken from the emitter also through a coupling capacitor. The voltage gain of a CC amplifier is approximately 1, and its main advantages are its high input resistance and its current gain. Notice that under SC conditions, the collector sits at ground potential. It's the common point between the input signal at the base and the output voltage at the emitter, which is exactly where the name common collector comes from. There is no phase inversion here, so the output is approximately the same amplitude and the same phase as the input. As we'll show, a CC amplifier gives us voltage gain close to unity, but always less than 1, a high input impedance in the hundreds of kiloohms, a low output resistance of just tens of ohms, and a high current gain. Because of this combination, the most common application of a CC amplifier is as a buffer stage, connecting a high impedance signal source to a low impedance load over a wide range of frequencies. To find the small signal AC model, we replace every capacitor with a short circuit, and we connect the positive terminal of the DC supply to ground. To keep the analysis simple, we are going to exclude the fixed bias resistors R1 and R2, but we will keep the source resistor Rs since it does affect our results. Now let's set up a worked example. Let HIC equal 1 kiloohm, HRC equal 1, HFC equal negative 101, and HOC equal 12 microsiemens with a load resistance RL of 2 kiloohms. These are typical CC amplifier values. Using these numbers, we are going to find four expressions: the current gain ratio AI, the voltage gain ratio AV, the input impedance Zin, and the output impedance ZO. We'll work through each of these one at a time over the next few slides. Let's start with current gain. First, some notation: VI is the same as VBC, II is the same as IB, VO is the same as VEC, and IO is the same as IE. With that, our H parameter equations become VBC equals HIC times IB plus HRC times VEC, and IE equals HFC times IB plus HOC times VEC. Now IE is defined as entering the emitter port, but the load current flows in the opposite direction, so IL equals negative IE and VEC equals IL times RL, which is negative IE times RL. We define current gain using the load current AI equals IL over IB, which is negative IE over IB. Since VEC equals negative IE RL, we can substitute into our second H parameter equation IE equals HFC IB plus HOC times negative IE RL, rearranging IE times the quantity 1 plus HOCRL equals HFCIB. Solving for AI, we get AI equals negative HFC divided by 1 plus HOCRL. Plugging in our numbers, negative 101 divided by 1 plus 12 times 10 to the negative 6 times 2 times 10 cubed. That works out to 98.6. Just a quick note, if we had instead defined current gain as IE over IB without the sign flip, its value would be negative 98.6. Now let's find the voltage gain. Since VEC equals ILRL, which is AI times IB times RL, we can write AV as VEC over VBC. From our H parameter equation, VBC equals HICIB plus HRC-VEC, which equals IB times the quantity HIC plus HRC times AI times RL. Dividing VEC by VBC, the IB terms cancel, giving us AV equals AIRL divided by HIC plus HRC AIRL. Now we substitute our expression for AI from the previous slide, and after simplifying we get the general result. AV equals negative HFCRL divided by HIC plus RL times the quantity HIC HOC minus HFC HRC. Plugging in our values, negative 101 times 2 times 10 cubed divided by 10 cubed plus 2 times 10 cubed times the quantity 10 cubed times 12 times 10 to the negative 6 minus negative 101 times 1. That gives us a voltage gain of 0.995, confirming what we said earlier, close to unity but just under 1. Next, input impedance. By definition, Z in equals VBC over IB. From our earlier equation, VBC equals HIC plus HRC times VEC over IB. And since VEC over IB equals AI times RL, we can write Z in as HIC plus HRC times AI times RL. Substituting our expression for AI and simplifying gives the boxed result. Z in equals HIC minus HRC HFC RL all divided by 1 plus HOC RL. Now let's plug in numbers. 1000 minus the quantity 1 times negative 1000 to 1 times 2000 divided by 1 plus 12 times 10 to the negative 6 times 2000. That works out to approximately 198.3 kilo ohms. That's a very large input impedance, and it's exactly the high input resistance we highlighted as one of the key advantages of this configuration. Finally, let's find the output impedance. To do this, we remove RL, set the input source voltage to 0 and apply a test voltage VEC at the emitter collector port with the input source suppressed VBC equals 0. So our first H parameter equation becomes 0 equals HICIB plus HRC VEC, which we can solve for IB. IB equals negative HRC over HIC times VEC. Substituting this into our second equation, IE equals HFCIB plus HOC VEC gives us IE equals HFC times negative HRC over HIC times VEC plus HOC VEC, which simplifies to IE equals the quantity HOC minus HFC HRC over HIC all times VEC, rearranging for the output impedance. ZO equals VEC over IE equals 1 divided by HOC minus HFC HRC over HIC. Plugging in numbers, 1 divided by 12 times 10 to the negative 6 minus negative 0.101, that gives us approximately 9.9 ohms. So to summarize all four results together, AI equals 98.6, AV equals 0.995, Z in is approximately 108.3 kilo ohms, and ZO is approximately 9.9 ohms, high current gain, near unity voltage gain, very high input impedance, very low output impedance. That's the signature of a common collector amplifier. Based on the typical values from our example, we can summarize the characteristics of the CC amplifier as follows. High current gain, a voltage gain of approximately unity, a power gain approximately equal to the current gain, no current or voltage phase shift, a large input impedance and a small output impedance. Now look at the practical circuit on the right. This is the emitter-follower configuration with R1 and R2 setting the DC bias point, Re as the emitter resistor, coupling capacitors C1 and C2 and RL as the load. Since the output voltage is taken at the emitter, it's in phase with the base voltage, so there is no inversion from input to output. And because there is no inversion and because the voltage gain is approximately 1, the output voltage closely follows the input voltage in both phase and amplitude, which is exactly why we call it an emitter follower. This circuit is often used as an interface between a circuit with high output resistance and a low resistance load. In that role, we call the emitter follower a buffer. Let's move on to a very popular two transistor configuration called the Darlington pair. It connects two bipolar junction transistors, so they operate as one super beta transistor, a technique introduced by Dr. Sidney Darlington back in 1953. The main feature of the Darlington connection is that the composite transistor behaves as a single unit with an overall current gain equal to the product of the current gains of the two individual transistors. For a BJT in the CE configuration, remember that beta equals delta IC over delta IB. The forward H parameter is HFE, defined the same way, delta IC over delta IB. So for small signal AC operation, beta AC equals HFE. For DC current gain, we use beta DC, which equals HFE equals IC over IB. Notice the lowercase and uppercase notation distinguishes small signal from DC quantities. Lowercase HFE is the incremental or a C current gain, while uppercase HFE is the large signal or DC current gain. Now look at the diagram. The emitter current of transistor Q1 becomes the base current of transistor Q2. So IB2 equals IE1, which equals beta 1 plus 1 times IB1. Similarly, IE2 equals beta 2 plus 1 times IB2. Combining these, the overall ratio IE2 over IB1 equals beta 1 plus 1 times beta 2 plus 1. That product is where the super beta effect comes from. Here we see the Darlington pair used inside an emitter follower configuration with the input coupled in through C1 and RB and the output taken through C2 across the emitter resistor Re. The primary impact of using the Darlington configuration here is an input impedance that's much larger than what we'd get from a single transistor network, which makes sense since the composite beta is so much higher. The current gain is also correspondingly larger, but just like the single transistor case, the voltage gain for a Darlington emitter follower remains slightly less than 1. It's still fundamentally an emitter follower. So unity gain is the ceiling, not the target. Our last configuration is the Sziklai pair. It's similar to the Darlington pair, except it uses two different types of transistors, an NPN and APNP, which is why it's sometimes called a complementary Darlington or a compound transistor. The current gain is about the same as what we get from a Darlington pair. The key difference is in how the two transistors connect here. The base current of Q2 is actually the collector current of Q1 instead of the emitter current, as it was in the Darlington arrangement. One advantage of the Sziklai pair over the Darlington is that it takes less voltage to turn on because only one base emitter barrier potential has to be overcome instead of two. In practice, a Sziklai pair is sometimes paired with a Darlington pair as the output stage of a power amplifier. This combination makes it easier to get exact matches between the output transistors, which improves thermal stability and gives better sound quality in audio applications. And that wraps up our look at the common collector amplifier and its Darlington and Sziklai pair variants. With this slide, we end the lesson on common collector amplifier. Work out the exercises given in textbooks and practice simulation using LT Spice simulator for better understanding of the BJT amplifiers.